right. I'm waiting for that projector to get fired up there. The class average on exam 1 was 70. The standard deviation was 15 points. So if you know anything about statistics, that means that if this was a normally distributed bell curve, if it was, then the class average was 70. And the distribution of the grades was something like this. Most people would lie within, what, 15 points of 70. And almost everybody would lie within 30 points of 70. So usually 2 standard deviations out is, if you're outside 2 standard deviations, then you're an outlier, which means you're either exceptionally on the high end or exceptionally on the low end. So take 70, subtract 30, and that's a 40. So if you're under a 40 on the test, that would mean that's exceptionally far from the class average. Or if you were 100 or higher, that would be exceptionally high. Make sense? All right, so the grades were, I've got a little summary here. We had 2 A's, we had 8 B's, we had 5 C's, 5 D's, 5 F's. And then if you actually look at the grade distributions, let's see here. Oh. The highest grade was a 99.3. And so you can see here the 2 A's and then the B's. So we had a couple of very high B's, almost in the A category. And then you had, these are all B's, and then we dropped to the C's, the D's, and then the F range here. So I think there would be reason for concern at this point. I think the break point would probably be here, right about there. Anything to the right of that, if your grade was to the right of that, I would just be a little concerned. You know, you're going to have to change the way you're approaching the class, the time you're putting into it. You know, if you've always studied a certain way and this is the result you're getting and it's not what you want, you've got to adapt, all right? Make a change. Now, these were the raw grades, so I did no curving or anything like that. I know that the test did run a little long, so I have another set of data where what I did is I went to each student and I dropped each student's lowest problem. I believe I have it. Where's my summary? And those are the grades in order. I can't find, I had a spreadsheet of what I did is for each student I went through and said how many got counted off, like for number 1, each student, and how many points I took off for each student. And from that I was able to figure out what problems were most commonly missed. And it wound up being the ones at the end, and I think it was just a time thing. So I haven't decided yet how I'm going to do it. I think if I change it where I drop your lowest problem, it benefits most of you. I think there's 2 people where it actually hurts them if I drop the lowest. I know that doesn't make sense, but that's what happens. And then the class average goes up to a 74 if I do that. So I'm considering that. I'm not locked into it. I actually haven't looked at this since I graded them, which was Friday? I think Friday morning I had them done. So, any questions? Your grade is on the bottom right-hand corner of the second page. Okay. For the most part, I mean, I was pleased with a lot of what I saw. A class average of a 70 on a Cal 2 exams pretty good. I think it's not bad. I don't make exams to try and get a certain class average. If everybody in here was capable of getting 100, I wouldn't make the next test harder. You know what I'm saying? These are the same tests I've been giving for too long, all right? And so I haven't really changed anything as far as difficulty. I won't ever change that for the class, if that makes sense. I won't make it any easier. If everyone's struggling, I won't make it any easier, but I'm not going to make it harder if everyone's doing well. So, no questions or comments, concerns? All right. In that case, we'll get back to the material. So hopefully you remember, Vanessa, do you mind hitting the lights again for me, please? Just turn them on. Yeah, thank you. Hopefully you remember that the last time that we were talking about things, we were in chapter 6, section 2, and I told you that there were really two parts to this section, what were called trig integrals and then trigonometric substitution. And there's a process for these, and I hope that at least when we did them in class that day, it seemed like y'all liked them. I don't know if the test reflected that so much, because everyone freaked out on the cosine squared one at the end, which was my idea of giving you a nice problem, you know, that would be quick, easy credit. That's what my goal was, but didn't quite work out that way. A lot of you tried integration by parts on that, and it was a disaster. But anyways, we are going to finish up the first part of section 6.2 and begin the second part of section 6.2. And there's a lot of information in this section as far as techniques and strategies. So what I did is copied and pasted those techniques and strategies out of the textbook, and I printed them out for you. So please take these and pass them around. I still don't know if you'll be able to use this on the test, your next test. I doubt it, but at least while you're doing your homework and you're getting acquainted with the material, you'll have something to go off of. All right? Y'all okay?
Who got the 99?
I can't tell you.
Just curious. I was just wondering.
No. I thought it was you. Wasn't you? Oh. You know, normally when I have, I'll tell you this much. Normally when I have a Cal 2 class, I always have students who have taken Cal 2 before, like they've seen it before. And a lot of times it'll be that student or someone who's seen it before that does the best on the test because, you know, it's their second time through. I can tell you the student who got the highest grade, this is their first time seeing Cal 2. So that much I can say. Okay, let me shut up and start getting back to the notes. So we had tackled problems, if you recall, that involved sine and cosine mixed together within an integrand. And we tried to address how we do that. And there were basically three techniques, and they are now here on this sheet on the top left-hand side. It says how to integrate powers of sine and cosine. You see that? It has three different strategies. Now what we're going to do is look at the column to the right of that. It says how to integrate powers of tangent and secant. That's where we are in the notes. There are two antiderivatives everyone here should just be automatic with, and that's secant squared and secant x tangent x. So we should all be comfortable with the fact that if we're ever looking at the antiderivative of secant squared, we learned from Cal 1 that that's tangent x dx, right? Or tangent x plus c, right? We're all okay with that. And the other one was if we ever had secant x tangent x, that's just secant x plus c because that's the antiderivative, right? That's the antiderivative because the derivative of that is that, right? What if you just have in an integral tangent x, or if you just have in an integral secant x? Do we know the antiderivative of those? They're on your table though, right? if you look at your cheat sheet, you should have the antiderivatives for all the trig functions that are raised to the first power. You can double check it yourself. You should see the antiderivative of sine is there, the antiderivative of cosine is there. Is the antiderivative of tangent there? What formula is it? Formula 12? It's kind of ugly. How about the antiderivative of secant? Formula 14? Antiderivative of cotangent by itself? Where's that? Oh, 13. Y'all see that? In your formulas, if you ever have any of the 6 basic trig functions by themselves, you're good to go, right? But these are special because these came from Cal 1. They are the derivatives of tangent and secant respectively. All right, with that in mind, we also need to remember that when we have a linear expression and function, remember when we integrated and we had a linear expression, we always had to scale by that a, the 1 over a in front, 1 over a in front, 1 over a in front. Okay, let's just keep in mind that we need that also. And then let's look at this technique. So I have the strategy up here, but I'm going to look at these 2 examples. With the secants and the tangents, there are only 2 strategies we have. The first one says what to do if you have the power of secant being even. The other strategy is what you do when the power of tangent is odd. All right? Those are the 2 strategies. I give you 2 examples. Each example is an example of one of those strategies. And then I've done a lot of the homework for this section. I have not finished it. If you watch the video of me doing the homework out of this section, when I get to secant and tangent, there's quite a few examples that I do with different variations of those 2 techniques. I'm falling a little bit behind on trying to keep up with the homework with the videos. I probably put about, I don't know, 3 or 4 hours into this assignment so far out of this section. And I'm still not done with the first half of the problems. So my plan is tonight I'm going to go up into my attic. I'm going to dust off my old 4x8 whiteboard. I'm going to put it up in my office and make some videos at home. I've been trying to do them here at work, but it's just not possible. So I'll get up to speed. All right, so we take a look at this. We see secant and tangent. We automatically start thinking this, right? We want to also make sure we don't have just like a real basic substitution. I don't see anything real basic, do you? Something that's derivative right away? No? But we do have a secant to an even power, don't we? And because of that, the technique says to do what? I'm going off of the handout. Karen, did you get it? You got one? Okay, well, I have them right here. What does it say? We're going to save a factor of secant squared. What do they mean by save a factor of secant squared? Peel it off, right? Peel off the factor of secant squared, because this is all multiplication. Right? I'm going to peel off a secant squared factor. Here it is. And then I'm going to use a Pythagorean identity back from pre-cal that said that secant squared theta, secant squared x they use here, equals 1 plus tangent squared x. You remember that from pre-cal? It's in your formula sheets also. And that identity allows me to, anytime I see secant squared, switch it to that. Now, why is it that they want us to peel off a secant squared? Secant squared is the derivative of what? That's the derivative of tangent, isn't it? So if I make a substitution in the problem, which they tell you here, but I'm trying to get you to think about it. If we make a substitution that u is going to be tangent x, there's its derivative, right? Doing a basic substitution. So du here, secant squared x dx, would allow me to begin to rewrite the integrand. Do we all agree that the secant squared x dx is du? Right? So I've got this taken care of right there. That's going to be du. How about the tangent to the fourth? What's that going to be? That's going to be u to the fourth. So I've got that taken care of. The only issue I need to deal with is the secant squared. Right? Secant squared, though, is that formula I just erased, right? And it allows me to switch the secant squared in terms of tangent, which means basically I can switch this in terms of u, because u is tangent. So this is the only part of the problem that's causing an issue. Why do I know that this is that I'm always going to be able to use the formula secant squared equals 1 plus tangent? How do I know I can use that formula? Because it's even, right? We said it was even to start with. And so if it's even to start with and I peel off a secant squared, this will still be even, won't it? Now, it may not be here, depending on the problem. If there were only 2 secants and you peel those off, then all that you would have was the tangent anyway. But guaranteed that that's going to be even. So using that identity, I'm going to rewrite the problem. Here we go. This is tangent to the fourth x, replacing secant squared with 1 plus tangent squared x, sorry. And then secant squared x dx. How are we going to rewrite it now? In terms of u. Yep. So we've got what? U to the fourth, 1 plus u squared, and then all of this, du. And that's just a polynomial, right? Distribute your u through, power rule, and we're done after we switch everything back. So u to the fourth plus u to the sixth plus c. I'm already integrating. What the hell? It's not right. Integral u to the fourth plus u to the sixth du. And that's 1/5 u to the fifth plus 1/7 u to the seventh plus c. Any questions? We okay? And last thing would be replace all your u's with tangents. So I'll write this one out. I think in the next problem, once I get to here, I'm going to stop and just assume you could do the rest. But just to make sure we're writing this properly, this will be 1/5. I need the u to the fifth power, so that's tangent x to the fifth power. So we put the 5 there, right? And then we do 1/7, and then we do tangent x again, and then to the seventh, and then plus c. Box it up. That's it. We good? Okay. Now, I'm just curious. I want to just do a slight adaptation to the problem. What if this secant had been secant to the sixth power? Then when I peel that off, what would have been here? 4. And then this could not be this. Right? What we would have to do is the following, and I do this on one of the homework problems, but I'm just kind of pointing it out now. Secant to the fourth x is secant squared x squared, right? So I would be able to rewrite this as secant squared. Where is it? I erased. Oh, here we go. This right here is secant squared, isn't it? But then I would have to do what to this? Square it here. And then that would change this to what? Squared here. And then could you distribute that through? Right here? Not yet, right? What would you have to do first? You have to multiply all that out, then come with your u to the fourth, and then do it. Okay, so that slight little change right here would make a difference in that part right there. Understand?
Yes.
Okay. All right, next one. On the next example, we're doing part B here. We have tangent to the fifth secant cubed. So can we use the first technique again of peeling off a secant squared? No. That's not what it says we should do. It says if what? Tangent is odd, right? If tangent is odd, I should do what? peel off a tangent x and a secant x together. So I have tangent to the fifth x secant cubed x dx. So I'm going to peel off a tangent and a secant, right? That's what the technique says. So I peel off, here I go. Tangent to the fourth x secant squared x, and then I'm going to put here secant x tangent x dx. See how I peeled one tangent and one secant over here? And then I know that this right here is the derivative of what? Secant. So that's going to be what I use for u. U is going to be secant x because the derivative of it is secant x tangent x dx. So let's see here. You need to start calling some names. You're doing a great job bringing your name things with you, and I'm not calling you on y'all. I need to start working on that again. So let's see. We'll start at this table over here. Any volunteers? Any Cowboy fans here? No? Alexis, are we not talking Cowboys today? No? Okay. You don't like the Cowboys anyway? Okay. All right. All I want to know here, anyone on this table, is how I can, what part of this can I rewrite in terms of u, and what part of it do I still need to address? So like, okay. So you've got these two pieces. What about that? What does the technique tell you anything else in there? Anything about a Pythagorean identity in that, or no?
Rewrite it to secant squared minus 1.
Says something about tangent squared. Yeah, so remember that Pythagorean identity that I had up here a second ago? That's what we used in the previous method, right? But if you keep tangent squared here and you move the 1 over, it's a different identity, right? It's the same equation, just looks different. So that's the same thing, right? So that means anywhere you ever see a tangent squared, you can replace it with secant squared minus 1. So we were saying the tangent squared is like, what do we do with it? Well, we're going to look, tangent to the fourth, what do we do with this? This was good, you said this was good. This one we have to work with. So write it as
Tangent squared x to the second power.
To the second power. So if we rewrite this as tangent squared x squared, and then just rewrite everything else, don't even worry about this. We've got this taken care of. Then, let's see, we'll go to the next table now. Any volunteers over there? Where? Nope, just secant. We're pulling a single secant.
Well, now you can put secant squared x minus 1 into it.
Yeah, well, yes, that's right. We want tangent squared x is going to be secant squared x minus 1. And if you do that, then everything is in terms of u, isn't it? Because u is secant. So replacing that, I'll do it up here. Replacing tangent squared x with secant squared x minus 1, and then it's squared, right? It has this squared on it. And then the next one is secant squared x. And then I have secant x, tangent x, dx. Okay, I'll give my table another opportunity here since it's all right. So so you want to tell me what it's going to be then? Hold on, give me a second to erase this. It's still an integral, right?
Yeah.
Okay, so what's it going to read?
U squared minus 1
Okay.
squared.
So the way you can say that, because we run into this a lot of times, you say u squared minus 1 quantity squared. So it gets a little weird because it's just language. I understand what you mean, but just to help you out. All right, so u squared minus 2 I mean, unit, u squared, shut up, Robert. U squared minus 1, that quantity squared. All right, and then this right here? U squared times u squared. And then this whole thing is du, so du. And now this is where I'll stop. So I'll say equals dot, 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 meaning you could do it the rest of the way. You would expand that out first. FOIL, right? This is not u to the fourth minus 1. It's not u to the fourth plus 1. This is u to the fourth minus 2u squared plus 1. Then distribute the u squared through. Then integrate power rule. Yes? Y'all are looking at me. Yes or no? Because I can do it if you want, but we're okay? All right. All right, so that's basically the gist of this whole method. It required this other technique, right? All right. There are some other cases, though, which are not so obvious, like these. Now, the first one and the second one are formulas, aren't they? The first one and the second one are formulas. You actually know what those are because they're formulas in the book. I'm going to show you how the first one comes about. It's really kind of easy. The second one, part B, much more challenging and very difficult, actually. The book explains how it's done, and it's not easy. But I'm not going to do it, all right? Because the book explains it. And you have the table. If you were ever on a test and had integral of secant x, you go straight to your formulas. That's what you do. But let me just show you how they get tangent, the formula for tangent. What should my answer be? Formula is formula 12. Natural log secant u, right? That's what I should get? Or natural log secant x here. So here's what I do. I'm going to turn it into sine x over cosine x. That's tangent. Anyone have an idea what to do with that?
Split the 1 over cosine x to secant x.
You want to do?
Sine x times secant x.
You want to do sine x times secant x? I could do that. I'll write it down. That's true. I could do that, right? But this has secants and sine. It doesn't have secant and tangent, right? All right, so just clear your mind. Sometimes you have to do that. What's that Office Depot or Office Max? You have that cheesy, what is it? Staples? Oh, Staples, I was wrong. Easy button. Oh, it's not a reset button? Well, then forget it. Just imagine a big red reset button, okay? You reset, wipe the hard drive for a second. No, don't wipe the hard drive. Just wipe the, the RAM, the cache, whatever. Start over. Basic substitution. Do you see something in its derivative? Okay. U is cosine x. Du is negative sine x dx. Do you see its derivative there? Yeah, it's up top, right? Oh, that's perfect. That's what I needed. I just need to take care of that negative, so I just put the negative on both sides. All right, so according to that, this integral turns into integral, but it's really like 1 over cosine, which is 1 over u. And then the sine x dx is really what? Negative du. So put the negative on the outside. Du. Y'all see it? All right, what's the antiderivative of 1 over u? Natural log, but there was a negative out front, right? So negative natural log absolute value of u plus c is my antiderivative. What's u? Cosine of x. Is that formula 12? 12? No. What's formula 12 say? It's not a negative natural log, is it? It's positive. So what did they do? I've warned you about this before. They put the negative up here on the cosine as a power, and then it made that cosine to the negative 1 turn into 1 over cosine. And 1 over cosine is secant. So that's how you get that formula. All right, that's how that one's done. Like I said, B is tough. Really, B came from, I don't know, just look at it in the book. They multiply by 1. They take secant x and they multiply it by 1, but it's a really, really clever one, not something that you would ever really think to do. And it's just someone figured it out that it would work that way. All right, but I will look at this last one here. Secant cubed x dx. So does this one fall into one of our methods? How to integrate tangent and secant. The first method says if secant is even, you do something, right? Do we have an even secant? No. It's not even, is it? So it doesn't look like that formula is going to work necessarily, right? Well, according to that, it won't work. So let me just show you this one, all right? And so, while I'm just setting this up, maybe someone can show me, or can look, is this a formula in your formula sheets? Is secant cubed on there or not? It's not on there? Okay. That's a hint of what I'm about to do. Right? Integration by parts. Now, I'm not going to do anything too crazy. Just think real quick about your dv choice and your u choice. You've got to be able to take the derivative of something, right? And you've got to be able to integrate something, and it's got to come from secant cubed. Any ideas? Secant for u, and secant squared x dx for dv, right? Because you can integrate secant squared, and you can differentiate secant. Perfect. Yes?
I have a question.
Yeah.
What about the secant squared? Can't you take a secant out, turn it into a 1 over cosine?
Mm-hmm.
You would have a secant squared?
Yes, but you wouldn't have the tangent that you need. So you're saying to refer to this method? Like if you wanted to try and create an even secant?
Right.
Yeah. It's kind of cheating because you're just rewriting secant a different way. That's all you're doing. You're not really changing the fact that it is an odd power of secant. Do y'all see this stuff? Okay, so let's fill out the table. What's the derivative of secant x? Secant x tangent x, right? dx. And then what is v going to be here? Go up. Tangent squared? Or tangent? Tangent x. Okay. We all right with that? All right, so this becomes ultraviolet minus voodoo. Secant x, tangent x, minus integral. Secant x times tangent squared x. And it doesn't appear that that got any nicer, did it? Does that appear that that got any better? But what? You get tangent squared. Pythagorean?
I wouldn't do anything.
Does this fall into our methods? No, because the method said if secant was even, we had something to do. If tangent was odd, I don't have that. So it looks like we got ourselves into a bind here, doesn't it? Appear that way? What I'd like to do, though, I did hear this, the Pythagorean identity, right? What is tangent squared x? Secant squared x minus 1, right? So just follow me here. This is going to be equal to secant x, tangent x, minus integral secant x. And then you said this was secant squared x minus 1? Is that right? Do you see what's going to appear over on this side? What? Secant cubed. Isn't that what we're trying to solve for? Didn't this happen? This was the rabbit out of the hat one. The secant cube is going to appear again, but something else is about to appear. Another secant, right? But they'll be separated. That's right. And do we know the antiderivative of secant by itself? it's part B, which I'm waving my hands at. I'm telling you it can be done. We're just going to use the formula for it, all right? All right, so let's continue. And since I know where this is headed, I'm going to go ahead and write the next line with the left side here, because I'm going to have to add on both sides. So I have integral secant cubed x dx is equal to secant x tangent x. And then distribute through here, I get minus integral secant cubed x dx. And then when I do the next one, I get a plus. And notice also I'm going to split it into two separate integrals. I could do them all in one integral sign, but I'm actually splitting it into two. Because I know what I'm about to do with this one, right? While I'm here, what is the antiderivative of secant x? Formula 14. Is it nice? Not really. This is going to be natural log secant x plus tangent x, isn't it? All right. So I've got that this integral, secant cubed, is equal to secant x tangent x minus the integral that I want, again, and then plus this integral, which is this. So what do I do now? Remind me, I forgot. Going to add that integral right there to both sides of the equation. And I do it over here also. So how many of them am I going to have on the left side? Two of them. Can I have two of the integrals? Yes.
Question.
Yep.
The plus integral secant x and the other integral, do those need to be in brackets?
And the other.
Together or in parentheses, like behind the negative?
I think I already distributed the negative. Because it was secant squared x minus 1.
Okay.
And I distributed the negative to both, and that's why this is a plus. Got it? Okay. I'm glad you're watching me, though. All right, so where am I? This side is what? Two of these? And then over here, this is still secant x tangent x, but then what? Over here? Plus natural log secant x plus tangent x. I'll go ahead and say plus c now, all right? And what would be left? What's left for me to do here? Divide both sides by 2. So I could put the whole thing over 2, or I could move my equal sign over, put a 1/2 in front, and slap a big parenthesis around it like that. So I'm just multiplying both sides by 1/2. Do I have to do 1/2 on the c? No, because it's still a constant. It doesn't matter. That's it. The antiderivative of secant cubed is that. All right, we good? We are done with trig integrals. Integrals that involve trig functions. By themselves or mixed together. Sines and cosines, secants and tangents. And now we move into the next topic, which is called trigonometric substitution. This is by far the harder of the two that we are looking at in this section. But everything we just did, okay, everything we just did with all these trig integrals was for a reason. You must be able to do this in order to do what we're about to do. All right, so let's talk about trig substitution. What does that say? After we what? Master. What does that mean? After we master the above concepts, we can use them along with an interesting type of substitution to find more antiderivatives of rather complex functions. These new types of substitutions. So you know how we've done substitutions in the past? We've said like, oh, I see something in its derivative. And we said u is equal to something, right? We've done that? We even used another type of substitution. It was integration by parts, where we let u be something and then dv be something else. So we've done different types of substitutions. This one is very different because it's not something you would think is going to get us anywhere, but it does. So these new types of substitutions we're about to do are called trigonometric substitutions, or as I'll refer to this technique as trig sub, right? Trig sub. The general idea is, and I'm going to read through all that, or I don't want to read through all that. Let me just explain in layman's terms what I'm saying there. If your integrand, that's the thing in here, involves one of these three expressions, there are three expressions. If that integrand has a square root of a squared plus u squared, well, hold on, what do I use on here? X squared, okay. X squared, square root, let me go in the order that they appear on this sheet. A squared plus x squared, or square root of x squared minus a squared. These are three different radical expressions, right? Where you have a constant squared, which is just a number, right? So you have like maybe 9 minus x squared, or maybe 4 minus x squared, or 25 minus x squared, or 3 minus x squared. It doesn't matter. This doesn't have to be a perfect square. It's just a number minus the variable squared. Underneath the root, if that appears anywhere in here, trig sub is what we're thinking. Trig sub. If you have the constant squared plus instead of minus variable squared, trig sub. If you've got the opposite order, variable before the constant, subtraction between them, you're thinking trig sub. All right? That's what gets you started. You have to see this in the integrand to be able to use it. Now, once you've actually determined which of the three it is, each one of these requires a different sort of substitution. So I'm going to go right to this problem right here, all right? Because this is an example of this first one being used. And I'm going to run through the process with you, and I'll refer to these notes once I start doing it. Are you all ready? I was hoping more for like the big huddle, everyone in the center. Are you all ready? The response I got there wasn't quite what I was. No. Okay. Clear the RAM. Basic substitution. Do you see something in its derivative? X cubed's derivative is in here, right? But see, it's trapped. It's a mess in there, right? We don't want the derivative of that being in there. How about the derivative of the whole thing in here, 16 minus x squared? Derivative of that is x, not x cubed, right? Unless you peel an x cubed apart, you might be able to do this, right? Maybe? So there might be a way. There might be a way with another technique. But isn't this also perfectly in that form that I said trig substitution is all about? Doesn't it have this somewhere in the integrand? Yes, you have that, don't you? Now, let's actually write down what we have. We have 16 minus x squared, which means that the 16 is 4 squared minus x squared, which means that the a for us is what? 4. So we have an a being 4. Agreed? All right. So what does this thing say I'm going to do? So reading this table, the way this table reads is the left column says, what expression do you have? Well, I have this expression, right? The next column says, what is the substitution that you would need to make? So what is the substitution that this is telling me I need to make? It's telling me that I need to use what? X is equal to what? A sine theta. Yes, x is equal to a sine theta. For us, what is a? 4. So we're really going to be making a substitution, x is equal to 4 sine theta. Now think about this for a second, what this technique is saying. It's saying you've got this thing in here and you're kind of having a little bit of trouble with it, right? Can't quite get it to work out. So they want you to come in here now, and everywhere you see an x, they want you to replace it with 4 sine theta. Now you may look at that and go, why in the hell would I replace something nice like x with 4 sine theta, right? I mean, that's going to make it more complicated, perhaps. But this thing was very, very well thought out, all right? Let's take a look at what happens if we do this. Everyone understand the substitution, where it's going to come from? Like how it's dictated, like how you determine what it is? Okay, so erase this. What I'm going to do now is, now that I've determined this is going to be my substitution, right? This is my substitution that I'm going to make. I'm going to write down that substitution just like we did before. And I'm going to differentiate this equation implicitly with respect to theta. Just do the derivative, right? Derivative left side, dx. Derivative right side, 4 cosine theta d theta, right? What I'm doing is I'm gathering information over here. I know I'm going to go over here and I'm going to replace every x I see with this. I know that I'm going to replace dx with that. See, this is not the substitution you're used to where you're trying to look for something in its derivative. No, you're just going to come in and change the problem into something that has trig stuff in it. And somehow it's going to work. All right, the next thing that you should do, and we have never done this before, is take a look at that special expression that made us choose this substitution. Wasn't that the part of this that made us choose this trig substitution? Let's talk about what this is. Now this table doesn't tell you what it is, right? Because I want you to actually know how to get it. Some textbooks, they just tell you what it is, but let's consider this for a second. Isn't this the same as 16 minus, now what's x? What are we saying x is going to be? 4 sine theta. What happens if you square 4 sine theta? What do you get? 16 sine squared theta, right? And what do these both have in common? 16. So you can factor 16 out underneath the root. And what's left when you factor the 16 out? 1 minus sine squared theta. What's 1 minus sine squared theta? Cosine squared theta. And what's the square root of 16 cosine squared theta? 4 cosine theta. Isn't it? And with that, we're ready to go. We're ready to do it. Any questions on where I got that? These are the things you'll do every single time you make a trig substitution. You see which one it is. You'll go off that table and you'll say, okay, I'm going to let x be whatever it tells you need to be. You'll differentiate it. Then you'll look at that part that has the square root in it, and you'll simplify it out, and it should turn out to be something really, really nice. And now we go over here and rewrite the integral. Here we go. I need to call on tables. So back table, Justin, Vanessa, Ruben, Kelly, anyone over there. What's x cubed going to be for me? 4 sine theta cubed. And let's take our time since this is our first one. 4 sine theta, the entire thing cubed, right? That's what x cubed is? All right. You want to keep going? What is square root of 16 minus x squared going to be? 4 cosine theta. Vanessa, you see that? Okay. So that's 4 cosine theta. Ruben, what's dx? That's right, 4 cosine theta d theta. We got it all? See it all? Let's clean this up. We have 4, this 4 is being multiplied times sine, it's being cubed. So doesn't that mean 4 times 4 times 4? Which is 4 times 4 times 4 times 4. Okay, so 64 times 4 times 4. All right, 4 to the 5th power. How about that? You like that? I have 4 to the 5th power, whatever that number is. Integral. So I took this 4, and the 4 cubed, took them all out of the integral. How many sines do I have in here? Just one, right? Sine theta, that's it. How about how many factors of cosine? Oh, wait, sorry, sine cubed. Ooh, bad boy. All right. I forgot the cubed on the sine. How many factors of cosine do we have? 2. Cosine squared theta d theta. And now, guess what? It's a trig integral now. So now you go back to the methods from the previous part of this section. You have sine and cosine mixed together, right? How do you deal with it when you have sine being odd and cosine being even? You're going to pull out a what? 1 factor of sine. I'm going to pull out 1 factor of sine now. You all understand how this works? This is the power of trig substitution, is that when you have an integral that is really nasty, you make this substitution that you think is going to be even worse, and it turns it into something that we can actually handle. Now remember though, our variable here is x, right? What variable are we in now? We're in theta now, so eventually we have to get back to x, don't we? Okay. All right, I need to continue this problem. Anybody figure out what 4 to the 5th is yet, or no? We'll just leave it as 4 to the 5th?
5,024.
Is it 5,024?
1,024.
Oh, 1,024. Integral. All right, you said pull 1 factor of sine out to the back near the d theta. Which means if I do that, what's my u going to be if I do that? U has got to be the cosine now. Oh, shoot. Now I've got u in the problem. So u is cosine theta now. Which means du is what? Negative sine theta d theta. Am I matched up good there? Need to tweak that a little bit? Negative, right? Negative du equals sine theta d theta. So let's see, we're moving up here. Justin, Ernesto, Karen. Can I rewrite this integral completely yet? Well, hold on. We're going around your next table. Yes, that's right. So this part you can handle. This is going to be what, u squared? This right here, sine theta d theta, is negative du. But the sine squared part needs to be converted. We need to switch that to 1 minus cosine squared. All right, so all right. I think at that point we're ready to write it out. All right, so now anything from my happy table here. You ready to rewrite this now? In terms of u, is it ready to go? All right, it will be, I'm waiting, negative 1,024 integral 1 minus u squared u squared du. So 1 minus u squared times u squared, that's du. Actually, that's negative du, which is why the negative came out here. That's a polynomial. What variable are we in now? We're in u now. We got to get back to where? X. But x got converted to theta first, right? So we got to go from u to theta back to x in the end here. Let's see. So this is going to be negative 1024. Oh, I can just go right through this, can I? All right, so this would have been what? U squared minus u to the fourth? So 1/3 u cubed minus 1/5 u to the fifth plus c. What do you think? We're not done, but what do you think so far? You didn't realize it was going to be this great, huh? Do you remember me having this talk with you about how quickly this subject builds on itself? This is what I mean, okay? So if you can't do trig sub, you can't do, if you can't do trig integrals, you can't do trig sub. It's that simple. All right, so let's go back now. I'm going to leave the negative 1024 out there. This is equal to negative 1024. All right, what was u? Because I forgot. Was cosine? Okay, so I've got 1/3 cosine theta, but then cubed, and then minus 1/5, and I've got cosine theta to the fifth, and I've got plus a constant. So I'm back to theta. Now I need to go back to x. Do you know what cosine theta is? Do you know what cosine theta is? So go back. What was your original substitution for x? What was it? X was equal to what? 4 cosine theta, wasn't it? Oh, it was 4 sine theta. Oh, shoot. So you mean I don't know what cosine theta is? I know the dx had cosine in it. But hold on. Hold on. This we know is true, which means this is true. You know where I'm going with this? Reference triangle. Sine of theta is what side over what side? Opposite over hypotenuse. Cosine of theta is what? Adjacent over hypotenuse. Can you get the adjacent? Yes, you can. It's what? Root 16 minus x squared. Now look, we could have cheated. We knew this already. If you look back in, remember when we wrote down those things? I did write at some point, I asked you what this was, didn't I? And we worked it all out, and we did a bunch of stuff, and didn't we get 4 cosine theta? Yes? So we did actually have cosine theta here. We could have just taken the 4 and divided it. And what is cosine theta here according to the triangle? Square root over 4, which is exactly what we got from that. But I'm showing you this because you need to be able to draw a reference triangle, because sometimes what comes out of here will be something like tangent theta. And then you can't go back to this information because it won't contain what you need, and so you have to draw the triangle to get the information you need. So we're there. We made it. We made it to the promised land here. Look, we've got negative 1024. We've got 1/3. Cosine theta is this over 4, right? This over 4. So we have root 16 minus x squared over 4, but then what? Cubed minus 1/5 root 16 minus x squared over 4, but now to the fifth, and then